Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 762, prime number of set bits in binary representation. This is an interesting problem that combines number theory with bit manipulation. We'll explore the problem requirements, analyze different approaches, and break down the solution step by step. Let's get started. In this problem, you are tasked with evaluating numbers in a specific range to determine how many of them have a prime number of set bits in their binary representation. Let's break this down. You are given two integers, left and right, which define the inclusive range of numbers you are working with. The goal is to count how many of these numbers have a binary representation where the number of ones, or set bits, is a prime number. Remember, a prime number is a number greater than 1 that has exactly two distinct divisors, 1 and itself. For example, 2, 3, 5, and 7 are prime numbers, while 1 and 4 are not. The constraints here are that both left and right must be between 1 and 10 to the power of 6, and left must be less than or equal to right. The output will be a single integer representing the count of numbers within the range that satisfy the condition. To illustrate this problem, consider the first example where left is 6 and right is 10. The numbers in this range are 6, 7, 8, 9, and 10. First, we convert each of these numbers into their binary representations. For instance, 6 is represented as 110, which has 2 set bits, while 7 is 111, which has 3 set bits. Similarly, 8 has 1 set bit, 9 has 2 set bits, and 10 has 2 set bits. Next, we check whether the number of set bits is a prime number. Here, 2 and 3 are prime, but 1 is not. Counting the numbers with prime set bits, we find that there are 4 such numbers, 6, 7, 9, and 10. So, the output for this example is 4. Now let's look at the second example where left is 10 and right is 15. The numbers in this range are 10, 11, 12, 13, 14, and 15. Converting them to binary, we get the following: 10 is 1010 with 2 set bits, 11 is 1011 with 3 set bits, 12 is 1100 with 2 set bits, 13 is 1101 with 3 set bits, 14 is 1110 with 3 set bits, and 15 is 1111 with 4 set bits. Checking for prime numbers, we see that the numbers with prime set bits are 10, 11, 12, 13, and 14, because 2 and 3 are prime, whereas 4 is not. This gives us a total of 5 numbers with prime set bits, so the output for this example is 5. To solve this problem efficiently, there are some important considerations to keep in mind. First, the range boundaries are large, as left and right can go up to 10 to the power of 6. However, the number of set bits in the binary representation of any number in this range will not exceed log 2, x, plus 1. This means that the maximum number of set bits we need to check for primality is 20. Since 2 to the power of 20 is greater than 10 to the power of 6. Additionally, when checking for prime numbers, we only consider values greater than 1. To handle the large range efficiently, we can pre-compute the primality of numbers from 0 to 20, which allows us to quickly determine if a given count of set bits is prime. This optimization ensures that the solution can handle ranges containing up to 1 million numbers without excessive computation time. To solve this problem, let's first consider a brute force approach. The main idea here is to count how many numbers in the range, left, right, have a prime number of set bits, or ones, in their binary representation. The steps are straightforward. We iterate over each number in the range, calculate its binary representation, count the set bits, and then check if that count is a prime number. For instance, if we find that a number has 3 set bits, we check if 3 is prime. If it is, we increment our counter. While this approach is simple to implement, it has some limitations. Its time complexity is determined by the need to process each number in the range and compute its set bits, which is O, n asterisk b, where n is the size of the range and b is the number of bits in the largest number. Additionally, the repeated primality checks make this method inefficient for large ranges, as we end up performing redundant calculations. This inefficiency highlights the need for a more optimized solution. Now, to address the inefficiencies of the brute force method, we can use an optimized approach. The key insight here is that the number of set bits in any integer is limited by the maximum value in the range. For example, if the upper bound of the range is 10 to the power of 6, the maximum number of set bits is at most 20, because 2 raised to the power of 20 exceeds 10 to the power of 6. This allows us to pre-compute which numbers up to 20 are prime, and reuse this information throughout the algorithm. The steps are as follows. First, we create a set of prime numbers up to 20. Then, as we iterate through the numbers in the range, we calculate the number of set bits for each number, and simply check if that count is in our pre-computed set of primes. If it is, we increment our counter. By eliminating repeated primality checks, this approach significantly improves efficiency while maintaining accuracy. The optimized approach offers clear advantages in terms of complexity. The time complexity is reduced to n, where n is the number of integers in the range, since operations like counting set bits and looking up primes are constant time due to the small, fixed size of the prime set. The space complexity is also 1, as we only store a small, constant amount of data for the pre-computed primes. This makes the solution scalable, even for large ranges. Another benefit is that we avoid redundant computations, which were a major drawback of the brute force method. However, there is a slight trade-off in terms of implementation complexity, as we need to include a pre-computation step for the prime numbers. Overall, the optimized approach is both efficient and practical for this problem. The optimized approach is the clear choice for solving this problem, as it strikes a balance between performance and simplicity. The key realization that the maximum number of set bits is small allows us to pre-compute primes once and reuse them efficiently. This eliminates the need for repeated checks, which were the main bottleneck in the brute force method. While the pre-computation step adds a minor overhead, it is negligible considering the small size of the prime set. Ultimately, this approach reduces computational overhead while maintaining clarity, making it the most effective and elegant solution for determining how many numbers in the range, left, right, have a prime number of set bits. In this problem, we need to count how many integers within a given range have a prime number of set bits in their binary representation. To solve this, we'll break the problem into smaller steps. First, we'll parse the input and initialize a counter to keep track of valid numbers. Then, to optimize our solution, we pre-compute all prime numbers up to 32, which is the maximum number of set bits a 32-bit integer can have. For this, we use the sieve of Eratosthenes, a well-known algorithm for efficiently generating primes. The sieve works by marking multiples of each prime number as non-prime. Once this pre-processing is done, we'll have a Boolean array where each index represents whether that number is prime, allowing us to perform quick primality checks during the main algorithm. This pre-processing ensures that we avoid redundant computations and maintain efficiency as we iterate through the range. Now, for the main part of the algorithm, we iterate through each integer in the range, left, right. For each number, we calculate its binary representation and count the number of set bits, which are the ones in the binary form. In Python, this can be done using the bin function along with count, 1. Next, we use the pre-computed prime array to check if this count of set bits is a prime number. If it is, we increment our counter. The use of the pre-computed prime array ensures that this check is performed in constant time. After processing all numbers in the range, the algorithm simply returns the final value of the counter, which represents the total count of integers satisfying the condition. This approach strikes a balance between clarity and efficiency, leveraging both pre-processing and iteration. The problem hinges on 3 key insights. First, the number of set bits in an integer corresponds directly to the count of ones in its binary representation. For example, the number 5, which is represented as 101 in binary, has 2 set bits. Counting these set bits efficiently is crucial, and while Python offers a direct method with bin number.count 1, other languages might rely on bitwise operations like repeatedly using number and number 1 to clear the rightmost set bit. Second, primality checks are optimized by pre-computing primes up to 32 using the sieve of Eratosthenes, which eliminates the need for repetitive primality testing during the iteration. Finally, the algorithm processes the range iteratively, examining each number individually. This brute force approach is practical here because the optimizations in set bit counting and prime checking reduce the computational overhead significantly. Analyzing the complexity, the algorithm can be broken into 3 main components. First, pre-computing primes using the sieve of Eratosthenes is very efficient, running in O, n log n, time where n equals 32, making this step negligible. Next, iterating through the range, left, right, takes O, right, left plus 1, as we examine each number exactly once. For each number, counting set bits involves O, log k, operations, where k is the number being processed. Combining these, the overall time complexity becomes O, right, left plus 1, asterisk log k, which is efficient for typical constraints. To ensure robustness, the algorithm also handles edge cases like single-number ranges, ranges with no primes, large ranges, and boundary values such as 0 or the maximum 32-bit integer. These considerations ensure the solution is both efficient and reliable under all scenarios. Let's walk through an example to solidify our understanding. Suppose the range is 5, 10. First, we pre-compute prime numbers up to 32, resulting in a Boolean array where indices like 2, 3, 5, and 7 are marked as prime. Now, we process each number in the range. For 5, its binary representation is 101, which has 2 set bits, a prime number, so we increment the count. For 6, its binary representation is 110, again with 2 set bits, so the count increases. For 7, the binary 111 has 3 set bits, another prime, so we increment again. For 8, the binary 1000 has only 1 set bit, which is not prime, so the count remains unchanged. For 9, the binary 1001 has 2 set bits, and for 10, the binary 1010 also has 2 set bits, both primes. The final count is 5, which we return as the result. This example highlights the efficiency of the algorithm and the importance of pre-computations in streamlining the process. This implementation solves the problem of counting numbers in the range, left, right, where the number of set bits in their binary representation is a prime number. First, we define a helper function as _prime to determine if a number is prime. This function handles numbers less than 2 as non-prime and uses a loop up to the square root of the number to check divisibility, which ensures efficiency. Next, we create a set of primes, prime_set, containing all prime numbers between 0 and 32. This range is sufficient because the maximum number of set bits in a 32-bit integer is 32, for the number 2 to the power of 32 1. The main loop iterates over each number in the range, left, right. For each number, we calculate the binary representation using Python's bin function and count the ones using .count, 1. If the count of set bits is in prime_set, we increment the count variable. Finally, we return the count as the result, which represents how many numbers in the range satisfy the condition. The algorithm is efficient due to the pre-computation of primes and the direct use of Python's built-in functions for binary representation and counting bits. Here, we start by importing the necessary utilities and defining our Java solution class. Inside it, we create a helper method called isPrime, which determines whether a given number is a prime number. This method checks if the number is less than 2, in which case it's not prime. For numbers 2 or greater, we iterate from 2 up to the square root of the number, and if we find any divisor, we return false. Otherwise, the number is prime, and we return true. Next, in the main method countPrimeSetBits, we pre-compute all prime numbers between 0 and 32, since the binary representation of integers will have at most 32 bits. Using a hash set, we store these prime numbers for quick lookup. This pre-computation helps optimize the process, as we avoid recalculating primes repeatedly. Finally, we initialize a variable count to 0, which will keep track of the numbers in our range that meet the required condition. Now, we iterate through every number in the range from left to right, inclusive. For each number, we calculate the number of set bits in its binary representation using the integer.bitCount method, which officially counts the ones in the binary form of the number. Once we have the count of set bits, we check if this value exists in the pre-computed prime set. If it does, it means the number satisfies our condition, so we increment the count variable. After checking all numbers in the range, we return the count, which represents the total numbers whose set bits count is a prime number. This solution is efficient, leveraging pre-computation and the hash set for quick prime checks, ensuring optimal performance across the given range. To solve this problem, we start by pre-computing all prime numbers between 0 and 32. Using a helper function called is_prime, we identify the prime numbers in this range as 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31. These values are stored in a prime_set for efficient lookup later in the process. Next, we iterate through each number in the range 6, 10. For the number 6, its binary representation is 110, which has 2 set bits. Since 2 is a prime number, we increment our count to 1. The next number, 7, has a binary representation of 111, which contains 3 set bits. As 3 is also prime, we increase the count to 2. For the number 8, its binary representation is 1000, with only 1 set bit. Since 1 is not a prime number, the count remains unchanged. Continuing with the range 6, 10, the next number is 9. Its binary representation is 1001, and it contains 2 set bits. Since 2 is in our prime_set, we increment the count to 3. For the number 10, the binary representation is 1010, which also has 2 set bits. Again, since 2 is a prime number, we increase the count to 4. At this point, we've processed all numbers in the range 6, 10, and the total count of numbers with a prime number of set bits is 4. Now, let's examine the next range, 10, 15. Starting with the number 10, its binary representation is 1010, and it has 2 set bits. Since 2 is a prime number, we increment the count to 1. For the number 11, the binary representation is 1011, which contains 3 set bits. As 3 is prime, we increase the count to 2. The number 12 has a binary representation of 1100, with 2 set bits. Again, since 2 is a prime number, we increment the count to 3. For the number 13, its binary form is 1101, which has 3 set bits. Since 3 is prime, we increase the count to 4. Lastly, we look at the number 14. The binary representation of 14 is 1110, and it contains 3 set bits. Since 3 is in our prime_set, we increment the count to 5. Finally, the number 15 has a binary representation of 1111, which contains 4 set bits. However, 4 is not a prime number, so the count remains 5. After processing all numbers in the range 10, 15, the total count of numbers with a prime number of set bits is 5. Lastly, let's consider a simple edge case where the range only includes the number 14. The binary representation of 14 is 1110, and it contains 3 set bits. Since 3 is a prime number, we increment the count to 1. With no other numbers in this range, the total count of numbers with a prime number of set bits is 1. Here, we analyze the time complexity of the solution. The first step involves pre-computing prime numbers for all integers between 0 and 32 using the is_prime function. For each number I in this range, the function iterates up to the square root of I to determine its primality. Since the maximum value of I is fixed at 32, the total work for this step can be approximated as the sum of square roots from 1 to 32. This summation is constant, as it does not depend on the input range. Therefore, the pre-computation step takes 1 time. Next, we process all numbers in the range from left to right, denoted as n. For each number, we compute its binary representation, which has a bit length proportional to log 2 of the number. Counting the number of set bits in this representation also runs in k, where k is the bit length. Since the maximum bit length is determined by the largest number in the range, which is right, this gives us a time complexity of n*log, right, for this iteration step. After counting the set bits for a number, the next step is to check if this count is a prime number. This is done using the prime_set, a pre-computed set of prime numbers between 0 and 32. Checking membership in this set is an O1 operation, and since it is performed once per number in the range, this step contributes n to the total time complexity. Combining all these steps, we have the pre-computation of primes taking 1, the iteration in bit counting taking n*log, right, and the prime checks contributing n. The overall time complexity is therefore n*log, right. Moving to space complexity, storing the prime set requires 1 space because it contains at most 12 elements. Additionally, temporary variables used during computation, such as number and set_bits, also require 1 space. Thus, the space complexity so far remains constant at 1. The binary conversion of a number using the bin number function generates a temporary string representing the binary form of the number. This string requires space proportional to the number of bits in the binary representation, which is O log number. However, since this space is used and discarded for each number during the iteration, it does not accumulate and only contributes O log number per number. Since there are no other space-intensive operations, the overall space complexity of the solution remains O1. Comparing this with a naive approach, where primality is recomputed repeatedly for each number of set bits without pre-computing primes, the naive method has a significantly higher time complexity. Specifically, the naive approach involves O and asterisk log, right, for bit counting and an additional O and asterisk sqrt, right, for repeated prime checks, making it less efficient than the optimized solution. Its space complexity, however, remains O1, as it does not require extra storage. With the optimized approach used in our solution, pre-computing primes and storing them in a set allows for constant time membership checks, eliminating redundant computations. This improvement results in a time complexity of O and asterisk log, right, and a space complexity of O1. Analyzing the best, worst, and average cases further illustrates the efficiency of this approach. In the best-case scenario, where left and right are close together, the number of iterations n is minimal, and the time complexity is dominated by the log 2 of the largest number in the range, reducing to O log right. In the worst-case scenario, where left and right span a large range, n is maximized, leading to a time complexity of O and asterisk log right. On average, the complexity remains O and asterisk log right, as it depends linearly on the range size and logarithmically on the bit size of the numbers. To mathematically confirm the time complexity, consider that the binary representation of a number has at most log 2 number bits. Counting the set bits involves iterating through these bits, leading to O log number operations for each number. With n numbers in the range, the total work becomes O and asterisk log right, where right is the largest number in the range. The pre-computation of primes, limited to a fixed range of 0 to 32, contributes a constant amount of work, O1. Combining these components, the overall time complexity is definitively O and asterisk log right. This analysis validates the efficiency of the solution and demonstrates how it balances pre-computation with iterative processing to achieve optimal performance. Now, let's address some common mistakes that arise in this problem. First, many solutions fail to efficiently handle prime number checks, as they repeatedly verify primality within the main loop. This can be avoided by pre-computing prime numbers up to a reasonable limit using the sieve of Eratosthenes. For example, since a 32-bit integer has at most 32 set bits, we only need primes up to 32 for this problem. Next, misinterpreting the binary representation is another frequent issue. Accurately counting the number of set bits is critical, and built-in functions like bin x.count 1 in Python or built-in _popcount in C++ can help ensure correctness and efficiency. Additionally, ignoring edge cases is a common pitfall. Special scenarios like ranges where left equals right, ranges with just one number, or ranges where all numbers have 0 set bits can cause incorrect outputs if not properly handled. Lastly, brute force methods over large ranges can lead to performance issues. For instance, iterating through every number in a range like 1, 10 to the power of 6, without optimization can result in timeouts. It's essential to incorporate bounded optimizations to address such cases effectively. Another common mistake is skipping the prime number condition. Some solutions incorrectly count all numbers with non-zero set bits, rather than restricting to numbers with a prime count of set bits. This directly violates the problem requirements and leads to wrong answers. Now, when it comes to interviews, there are several insights to keep in mind. Problems like this often reward a strong grasp of bit manipulation techniques, such as using bitwise operators like AND, as well as specialized functions like popcount. Practicing these concepts can give you a significant advantage. Optimization is another key area. Pre-computing values like prime numbers helps reduce redundant calculations during range queries. It's also important to stay mindful of constraints, such as the maximum number of set bits being 32, which limits the prime numbers you need to consider. Adopting a modular approach to the problem, breaking it into smaller steps like counting set bits, checking primality, and iterating through the range, can make your solution easier to debug and explain. Finally, be prepared to discuss trade-offs, such as how pre-computing primes trades off higher memory usage for improved runtime efficiency. This problem connects to several related problems that can help deepen your understanding. For example, LeetCode 191, number of 1 bits, focuses specifically on counting set bits, which is a key step here. LeetCode 204, count primes, deals with efficiently identifying prime numbers, which ties directly into this problem's requirements. Another interesting variation is LeetCode 784, letter case permutation, which emphasizes combinatorial thinking similar to the binary representation aspect of this problem. Now, when considering alternative approaches, the brute force method is a straightforward starting point. With this approach, you iterate through the range, count set bits for each number, and check if the count is prime. While simple to implement, its n*k time complexity, where n is the size of the range and k is the average bit length, makes it impractical for large ranges. This approach is more suitable for understanding the problem but not for optimized solutions. For a more efficient solution, the optimized sieve approach is highly effective. Here, you pre-compute prime numbers using the sieve of Eratosthenes, allowing for quick lookup during range iteration. By combining this with set bit counting, you achieve a time complexity of n plus m log m, where n is the range size and m is the upper limit for prime computation. This approach is faster overall, though it does require extra space for the sieve. Another alternative is the bitwise manipulation approach. Instead of converting numbers to binary strings, you use bitwise operations like x and x1 to count set bits. This can be combined with pre-computed primes for even greater efficiency. While the time complexity is comparable to the sieve method, bitwise operations often reduce constant factors, making the solution slightly faster in practice. However, this approach is a bit harder to implement and may require additional debugging effort. Both methods balance speed and memory usage, offering flexibility depending on the problem constraints and your familiarity with the techniques. Great job! We've successfully tackled the problem and explored efficient approaches to solve it. Remember, this problem is a perfect blend of bit manipulation and number theory, so practicing similar problems will strengthen both areas. Thanks for tuning in, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!